Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Elaborate introductions. Welcome back. Sylvia, who, for those of you who don't know, Sylvia Calderon, who's doing a PhD in Edinburgh University with Paul Palmer, who's a visiting researcher here, and Drew Purves. You did an internship here about 3 years ago?
2 years, something like that.
It's about long
Not
ago.
that old. Yeah, it's almost 2 years
That's when
now.
I was doing my summer school, so it's a year ago, a little over a year.
I'm pretty sure our opinions have spanned from 3 years to 6 months.
A while ago.
And you're going to talk about where you're up to now.
Yes,
Towards the end of
that will do.
towards the
Hopefully.
book, anyway.
So what I'm actually going to talk about is a global phenology model, which is what I've pretty much been working on since I left here after my internship, whenever that was.
What did you say you were going to work on before you arrived here last
I don't remember. It probably was this. I hope it was this, because otherwise I'm just going all over the
Weird for a
place.
PhD, isn't it?
Yeah. So what I'm going to do is tell you what is phenology, why we should care about it, how does it apply to any other kind of work in the big global scales, and then go through what people have already done in this field, because obviously it's not new, and then try and tell you where I was trying to get to, what are the reasons behind building this specific model, and then tell you how the model works and show you some global results I have. So, phenology so the word phenology in general describes the timing of biological processes, and phenology specifically refers to the seasonality of leaves, so the time when leaves appear on trees and when they fall off. And traditionally, people everywhere, mostly in botanical gardens and in forests, in temperate regions, have been looking at the date of bud bursts, when the very first leaf appears on trees, and when leaves start to fall. And more recently, people have been looking at the length of the growing season, because the idea is that as the globe gets warmer because of climate change, the growing season will get longer and longer, which is, as I will show you, a hypothesis, because we don't actually understand what's going on. So why should we care? We talk about climate change, we talk about CO2 in the atmosphere, we talk about the biosphere taking up CO2, so it's a sink of CO2. And to do that, we have global carbon models and climate models, and then further on we can look at atmospheric chemistry. And eventually, if you look at those models, in the end, it comes down to vegetation, to terrestrial vegetation. And one of the things it does come down to is how many leaves do we have on those trees, because that's obviously important first for primary production, because leaves are what take up carbon and transform it into organic matter. And then for climate models, the number of leaves changes the surface albedo and the surface roughness. So it's a big impact on the global climate. And in terms of atmospheric chemistry, trees also emit a number of other things like VOCs. And that's all also obviously influenced by the number of leaves we have. So we need to know this. And the input that all of this, or most of this this model take, is leaf area index. And leaf area index is just a number of one-sided leaf area per unit ground area. So it's just a measure of how many leaves we have. And if this is what we need in terms of seasonality, then suddenly what we had before, when I said we had start of growing season and end of growing season, is not enough, and we need something else. So how do people look at phenology? The state-of-the-art model, which was first built in the 1700s, is called the degree day model. And what it says is, in temperate regions, for deciduous trees, once it starts getting warmer and the temperature gets above a certain threshold for a certain number of days, leaves start growing. And then in autumn, you have the opposite, and when it gets colder, trees drop leaves. And you can have an addition to this in terms of day length, depending on the model you're looking at. And this is what most people use as their phenology model for whatever they're looking at. But there are several things that are wrong with this model, or not necessarily wrong, but not very useful. So one thing is it applies to temperate regions, but we want to look at the globe. Another thing is it gives you a start and end date, but what happens around here? What happens in the middle? Where does it go? If we want LAI at every time step, then this model doesn't tell us anything about what's going on. And another thing that this model isn't very useful at is explaining what's actually going on in the leaf and in the forest. Because this is a fairly arbitrary threshold, and it's just something that people have observed, that when it gets warm, you get leaves. But this isn't a physical explanation for why trees add leaves there. So I decided to look for something else that is not the going degree day. So ideally, we want a model that explains what's going on and gives us a reason for why trees would add or lose leaves at any point. And that can also be used to explain other things on the globe. So ideally, we want this model to be global, so to apply everywhere. We would also want it to be biome independent. And by this I mean we shouldn't have a separate model for temperate regions and another model for tropical regions and a model for wet regions, dry regions. I just want a model at the global scale. We also want the model to be relatively simple, because if we want to use it with Earth system models, then those already have a large number of parameters. If we add another 20, 30, then it's not going to be any use because we don't have enough data. And lastly, I want the model to have predictive capabilities. If we want to explain what will happen in the future if the climate changes, I don't want the model to be dependent on the conditions now.
That's about bioindependence. I understand the elegance of that, but you could say, well, we want at least to capture the biomes because they capture the largest, most obvious pattern in phenology globally.
Yes, we want to capture the biomes, yes, but we don't want it to need that information at the start.
We biome to be a parameter.
Yeah, exactly. So obviously we also need data. If we just have a model and no data to parameterize it with, then that model isn't of any use. And traditionally, data, as I've said, were just eyewitness observations. They were local, they were species specific, and while this is useful, and it gives us a trend and information about when leaves start coming out, is not useful at global scales. And we also want a continuous data set, both spatially and temporally, to give us enough information for a global model. Now, if we look at satellite-based data, which is available since 1981, I think, it's global, so it's everywhere, and it's continuous because obviously satellites keep going. And what it is based on the leaf properties in terms of reflectance. So leaves will absorb light in the red region of the spectrum, but they won't absorb at all in the near infrared. So just based on that ratio, we can tell how green a certain region is, which gives us information about how much vegetation we have. And the data set that I've used to fit this model is a MODIS LAI, and MODIS has been in orbit since 2000 and is measuring continuously. And it has a base spatial resolution of 1 kilometer, which I've averaged. So I don't actually use 1 kilometer, but it could be used at that level. And it's not simply a ratio of reflectances. it's also corrected for vegetation structure and soil reflectance, so it gives us a more accurate image of the actual number of leaf layers.
Question
Yes.
in relation to that, in relation to modus. I remember in putting together our own simple phenology model that it would be nice to be able to use the modus data and going to the modus data set, seeing all the different packages and all that. This is a big study in itself, pulling this off.
Yes, it is.
I mean, that was my impression, but how easy is it for an everyday ecologist to have access to this data and actually use it?
It's not straightforward in any way. So the information in there is really easy to use, but to get to the database and the file formats and the different grading, it's quite complicated.
So do you think that it should?
It should be in
Not
another
necessarily.
format and it should be more accessible. I
I
don't.
should do that.
The fetch mode is,
Fetch modus.
Yeah.
Fetch process.
Because they've tried various things, none of the tools they give works very well. So I think it's up to the user to do something about it.
And in relation to other data sets, I might want to turn to satellite-based data for phenology patterns and things like that. Modus isn't the only one that's there.
No, so another one is the AVHIR, which is a long-standing one that's since 1980s. I think it has a coarser spatial resolution than Modus, and it's not as accurate. It has more sources of error because it's older.
Okay, so you prefer modus.
Yeah, there's also Spot, that's a European one. There's Landsat, which has now broken down. So there's various things, but in terms of how accurate it is, I go for Modus.
Modus is better for earlier.
Yeah.
Modus has the highest temporal resolution.
Yeah,
highest
that's true as well.
Spatial temporal resolution Modus has. Landsat has a higher spatial resolution, but temporal resolution.
Yeah.
AVHR is same temporal, but much coarser spatial.
Yeah.
And then Spot is the French. So do with that what you want.
Yeah.
Yeah, thanks.
Well, indeed, given the independent satellite data on, perhaps if you can look at the same phenomena with these different satellite data sets, you could get a really accurate estimate and infer how much error is coming in from the different.
Yeah, it's the problem is you're not always looking at the same thing,
Yeah.
and not even with the same satellite because of the orbit and the swath, and it could be done, but it's not as straightforward. It's just taking one thing,
Yeah, right.
but it could work.
Right.
Right. So now that we've got an idea of what we're looking for, let's look at the data. So I've chosen one site. This is just an average yearly time series. I've chosen one site in the Amazon that's a tropical wet forest, and one site in tropical Africa, which is supposed to be drier, and then the eastern US, which is mostly deciduous, and the boreal evergreen, which I will get to in a bit and explain stuff about it. So what are we looking for? When do we observe the peaks? In tropical regions, we know that there's a dry and a wet season, and the difference between the dry and the wet is obviously precipitation, is precipitation, as the name says, and it's also light availability, because in the wet season, the cloud cover is so heavy that the light environment changes. And we can see that in the Amazon, where there's enough water in the soil to sustain vegetation, we observe a peak at the maximum light levels, so it seems to be light limited, whilst in the drier tropical regions, it's the opposite, so those are water dependent. Also, if we look at temperate regions, we do know that there is a temperature threshold, but we can also observe that the peak occurs at the maximum light levels. And the light environment here changes not because of cloud cover, but because of day length, because obviously the period with sunlight is a lot longer in summer. So this kind of tells us we should be looking out for light and water and possibly a temperature threshold in all regions, because I'm just trying to find the common things that we can put together for tropical and temperate. And then finally coming to the temperate evergreen, this is what MODIS shows. It's nothing like you would expect it to look, unfortunately, in tropical evergreens. So you would actually want a higher LAI with a small seasonal amplitude. So I'm not...
You mean temperate evergreens?
Yeah. Is that what I said? Sorry.
Even like years.
Yeah. Yes. So in the boreal, so in the high latitude evergreen, it shouldn't look like that. So I'm not going to talk very much about this because I'm not sure how much information we can get out of the data. So anything.
Is that reflectance problems that MODIS has?
It's snow problems. So it doesn't flag snow properly, and it's stuck there.
Would any of the other data sets help you there? I mean, the satellite ones.
They would still, well, to be the same snow problem, unless they have better snow flags.
I was going to say, have you looked, because I've seen people have been doing, there has been a lot of work on MODIS snow masks because of that problem.
It's a bit tricky though, because in applying the mask, what you might basically say is, you might just get the middle bit of that curve and then get no data.
Yeah.
And so, which is not much more helpful really. So, and then even if they try and correct it more, chances are what they would do is they'd have the answer in mind and fiddle with it until they get the answer they want. So, you know, it may just be one of these things. You have to accept limitations, don't you? And it may simply be that satellite observations of LAI with current technology are just not very useful in that biome, right?
Well, it's snow in the canopy, because around here you're going to rather than having a full snow cover, you are going to have some patches of snow in the existing canopy, and there's no way to get through that.
Can you easily carve out the areas of the world that are very likely to estimate very well? The ones you would say they'll likely to do.
Well, given a land cover map that I can trust, I probably can, or just cut out the higher latitudes.
Are there any other environmental problems that can be caused as well? I don't know.
Really, xeric site should be bad, right?
I don't know. It's so the data I'm presenting is already filtered out because I provide masks for cloud and aerosol and snow. Yeah. So I've already filtered out everything that looked that would be really bad. Beyond that, I don't really want to throw away any more data. Just to keep it simple. So yeah, that's the data. What do we do with it? I want to look at phenology from the point of view of carbon and the carbon optimality model, because that's what leaves do. And given an unfavorable season, what trees can control, most of all, are leaves, and when they drop them and when they gain them, because they're not going to change the whole structure of the forest during winter and then rechange it again in summer. So they're going to control leaves. So I'm going to assume that trees try to achieve an optimal LAI given the conditions they have at any one time by adding leaves. And this is a big decision, because you, as a tree, you have to decide when you're going to invest the energy and material into building a leaf. This is important. If you take this decision too early, you're going to lose a lot of resources. But once you've done it, you can keep the leaf until it's no longer efficient. So if the carbon the leaf produces is not enough to sustain its own needs, then the leaf can be thrown away. And starting from that, how can we put this into equations? So let's think about an optimal LAI. If we start in a temperate zone with a forest that doesn't have any leaves, and suddenly the temperature goes above 0, and there is enough light around, it can start adding leaves. And the more leaves it has, it will have a higher surface for absorbing light, and hence producing more carbon. But obviously, the more and more leaves you get, the darker it will get at the bottom of the canopy. So that there'll be a point if you add any more leaves at the top, the leaves at the bottom won't be able to photosynthesize anymore because they will have reached their compensation point. And that's what I term the target LAI. And it is the point where simply the light at the bottom is equal to the compensation point of the leaves. And we can obtain that simply by using Beer's law of light attenuation through the canopy. And we get that. So at any point in time, if the number of leaf layers is below this target, then the trees decide they can add more leaves, and they'll keep on adding. If it's not, it will just not add any more leaves. And that's all there is to leaf gain everywhere. If we talk about leaf loss, we've said that we want the point where assimilated carbon by a leaf is lower than what the leaf consumes, so respiration and any other maintenance costs for the leaf. So how do we write out carbon assimilation? In its simplest form, this is the light use efficiency curve. So the more light a leaf receives, it can capture more carbon until it reaches saturation because of the photosynthetic mechanisms in the leaf that simply can't go any faster for the leaf. So we can just write that as a linear relationship between assimilation and light with an Amax. And here, if we talk about light, we talk about the entire light absorbed by the canopy in the photosynthetic active region. But light isn't the only thing that affects carbon assimilation. One other thing we need to look at is the water level. Because for a given amount of water available to the tree from the soil, the tree can adjust its water uptake and its water loss by closing the stomata in the leaves. But what it loses by closing the stomata is the uptake of CO2. So if they don't have enough water and they are forced to close their stomata, then their carbon assimilation will go down because they can't take in CO2. So we describe that by having an adjustment factor, where we say that there is a soil water level for which carbon is not affected in any way, and that's W max. And once the water level goes below W max, the photosynthetic capacity of the leaf will start decreasing linearly until it reaches the W mean, at which point the stomata have to close and photosynthetic shuts down completely. And theoretically, we don't want to get to that level, so we're going to start losing leaves somewhere around here, so it doesn't completely die off. The problem now is that both W min and W max are dependent on the number of leaves you have, because the more leaves you have, you're going to lose more water, and you're going to need more water as well. So the way we describe that is, if we first look at W min, by definition, the way we've put it into the adjustment factor is the level at which all stomata have to be closed. So there's no evapotranspiration, and that's simply equal to the water use per leaf area. And then for the W max, what we're looking for is the absolute maximum stomatal aperture. So that will have the plant water use plus maximum evapotranspiration per leaf area. And if we substitute those into the first equations, we simply get this, which is, so it will have the same shape as this, but it will be different for the different number of leaves. So that's how water impacts carbon assimilation. What else do we have?
Sorry, Selsa, just to understand this, I think what would happen then is that if, for instance, they had too many leaves, that would make the W min and max greater. So
so they will need more water.
Right, so then they could be, for instance, suffering and then they might start to drop leaves.
Yeah.
And then as they drop leaves, the W min and max would drop, so that the remaining leaves are no longer suffering.
Yeah.
And then they might stop dropping the leaves.
Yeah.
So that's how they would adjust their LAI
Mhm.
in
Yeah.
response to soil moisture.
Does that make sense?
Yep.
All right.
Totally.
That's good. Yay. All right. What else affects carbon assimilation? Assuming there's no outside stress, there's enough light, there's enough water, the temperature doesn't go below 0. What do we need? What else are we left with? Well, leaf aging, and this happens in the tropics, that if the leaves stay on for long enough, the photosynthetic mechanisms will start decaying, so then the photostatic capacity will go down. And ground-based measurements have shown that what happens is you get a new leaf, which will have very low photostatic capacity, which will go up very fast to its maximum, after which, if it stays on for long enough, so in temperate regions, what happens is it will stop somewhere around there because of various outside constraints on the leaf. So it will never get to the bit where the photostatic capacity starts decaying. But if there's no outside pressure, it will get to an age where it's too old and it will need to be dropped just because in itself it's inefficient.
This guy Kikuzawa
Yeah.
says that initially he assumes that it declines from the minute the leaves are born. So, they bang up to maximum capacity and that declines linearly with age. And he has some evidence, not necessarily, it's difficult to say whether it's linear or exponential decay, but it starts declining very shortly after. The tree leaves are out, but that's temporary. But the data is very scattered.
Yeah, I have my doubts about that. I've seen that he says that, but it would have to be a very slow decay. So for leaves that stay on for 3 or 4 years, it would have to be a very, very slow decay. So this kind of curve makes a lot more sense to me.
I think the implication is the decay rate is related to the age of the maximum lifespan of the leaf itself. So short-lived leaves, which tend to have a high photosynthetic rate, also tend to have a rapid decay rate of photosynthetic capacity through time.
Yeah.
Part of the function being heat and stuff like that. But like temperate leaves, flimsy temperate leaves get thicker over time. You might imagine their photosynthetic capacity goes down as they're becoming.
Yeah, but they don't stay on for that long.
No.
It's not. You don't really. I don't think you would see that much decline in photostatic capacity. I think it'll just be stuck somewhere in there.
How much data have you got?
For this.
What data did you look at?
There's very few papers, about 4 of them. I can show you the papers, but
one question is whether
yes.
it actually matters at all, which way you have.
Yeah, I don't know. So this is important in the topics. It comes out as a big impact in the topics.
That's really.
So that's where we really need to care.
Which is where you have your longest stage leaves.
Yeah, because there's nothing else to make the leaves fall. They're not stressed by anything. So I know this matches what I think happens. I know. So if we have those adjustment factors, we can then calculate the final carbon assimilation. And then at every time step, if that assimilation is smaller than a limit, which will also be a parameter, then those specific leaves drop. So that in temperate regions where all the leaves come out at the same time, we don't really care about age and they'll all drop at the same time, while in tropical regions, you'll have different cohorts coming out at different times and they'll drop at different times because of the age constraint. All right, so as a summary of the way we use the model, is the first input is photostatic active radiation. Given that, you calculate the optimal LAI. If needed, you add more leaves. If then you calculate the total assimilation given the water constraints and age constraints. If needed, you lose those leaves, and then you calculate the final LAI value. That easy. So we have 10 parameters. 10? Yes. 12, sorry. So we have 12 parameters for the different things. And what I've done is I've taken this model and fitted it using the MCMC, the fields back method, using the MODIS LAI for the actual leaf area values. Then photostatic active radiation and temperature from the geosphere dataset, and soil moisture from NCAR. I was, in terms of spatial scales, I was constrained by the PAR, which has a spatial resolution of 2 by 2.5 degrees. So fairly coarse, and I fitted it to that. And everything else is spatially averaged to that spatial resolution. So I've taken it all, fitted it, and here are some results. So these are predicted values for 2000-2005. We have the mean LAI, which shows, as expected, the highest values across the tropics and then lower values in temperate and boreal regions. In terms of seasonal amplitude, we've got the high seasonal amplitude in Europe and the east coast of America, where we know there are deciduous trees. And then the lowest amplitude in tropical regions where we don't find that much seasonality. In terms of timing, this doesn't actually show that much without any information on things like precipitation and temperature. But obviously, the maximum will be in summer in the northern hemisphere for temperate regions. And there's not that much of a gradient with latitude for boreal regions. If we compare this with the MODIS data, so this is just a relative difference. If gray means that we're right at the value we're expecting, cold colors mean that the model is underestimating, warm colors mean the model is overestimating. So for the mean, it gets...
I was going to say, so the fact that your scale is only on minus 0.6 to 0.6 and minus 1 to 1 says a lot in itself. I mean, you obviously don't have any major deviations, really, do you? Cause,
yeah.
Because otherwise it would be on a scale of minus 2 or 3 or 4 or whatever. Because, you know, with the LAI amplitude in the temperate zone being in the 0 to 5 range, something like that, being accurate to within 1 across the whole of the temperate zone with that simple model is pretty good.
It's relative.
It's relative. So it's relative to the observed.
Oh, it's
it's predicted minus observed divided by observed.
Okay, well, that was a bit different from
I don't think I should interrupt you.
So one would mean 100% more than the observed.
Yeah,
and minus 1 would mean 0.
Would mean 100% less than the observed.
So yeah, so 0 LAI.
Yeah. So in terms of mean, it's underestimating for temperate regions. And I'll show some time series where that's really obvious.
I remember you asking about how you might show these things.
Yeah.
With that global map. I'm just thinking you could use one of those Holdridge diagrams or climate diagrams. So you plot, say, mean biotemperature on one, mean precipitation on the other, divide it up into the different biome regions of the world, and then you could sort of summarize those plots from that. I mean, it's good to see on the globe as well. But you'd like to see whether it's being systematically over or under predicting for certain types of vegetation.
Yeah, well, it does come up in terms of latitude. So in terms of so for amplitude, it underestimates amplitude in tropical regions, which we had with a solely tropical model as well. And I think that's because of noise in the data due to cloud.
Right.
What color is the eastern US? Sorry, was that like blue or black?
Pretty grey.
It is close to grey.
Okay, so it's right around here.
Yeah. So that's good. The amplitude for temperate regions is fine. It's a mean for temperate regions. It's slightly underestimated. And the timing is pretty good everywhere. There's no obvious discrepancies. Wow.
It would be, I think this is what you were saying. It would be nice to break that up by
Climate.
Yeah.
biomes, ecoregions, something, because
Yeah.
So it would give you
Yeah, it will give more information than what I've just done here. So sure, I'll tell you that. Other information we can pull out of the model is what's limiting leaf growth, because I didn't give it any biome information, but I can take out biome information. So red regions are temperate regions where leaf loss is triggered by low temperatures and low light levels, and then blue is regions where water is what's limiting, and then whatever's left is just leaf age. So we obviously see at high latitudes, it's always temperature. Tropical regions is age, and there are actually very few regions that come out to be water limited. So subtropical Africa and parts of East Asia, of Southeast Asia, sorry. And I think that's a lot less than people usually expect in terms of water. So a lot of people talk about water limitations in tropical forests, but I don't get that many forests that are water limited.
It'd be good to talk about that though, because you don't. Your model kind of has like a sort of continuous relationship with water in a way, doesn't it?
Yeah.
So it's not, because we did talk about having a model that just had hard and fast, like limiting factors. So in which case you've got an unambiguous idea about basically what's limiting, at least at one time of year in one place. Whereas in your model, all of these things interact, don't they? So you must have done something to sort of say which is the most important of these three, or
so
something.
The way I've built this is if there's any point in time where the leaves drop without the water or with the water when you calculate the assimilation. So if the assimilation drops below the limit without the water adjustment factor or without the age, then it's what's limiting. But you are right, it's a continuous thing, so there will be combinations of
so
three.
it might be that the water has much more important effects, but they're more, it might be the second most important factor in a lot of places, and it's in there in the model, but it's just not coming out as a major factor in these places, I guess.
Well, there could be different ways of plotting this map, so this is just one.
Yeah.
You could probably get more information out of it.
I suppose another way to do it is you literally do a global simulation, just making water really high everywhere or what have you, and then looking at the differences and so on. So there'd be different ways to do it. Yeah, because I suspect from what you said about your model, because it doesn't, it's never, unless they're below. It's only when they're below W min that you'd actually say, well, the thing basically.
That's why it kills them.
In reality, at that point, probably all the leaves die straight away. But before that, they start dropping them in a way that means that they actually don't experience the water stress that you might think, because they adjust the LAI down. So you can kind of imagine that something like that's actually happening, that actually the water could be quite important, but there's not actually that much water stress because the plants, because they're clever.
Because they know when to drop leaves.
It seems hard to believe that the vast amounts of Mokani in southern Africa aren't being true, that that the interannual variation that you see there is not at least strongly linked to the wet and dry seasons.
And actually, there is a peppering of blue sites there.
Yeah, exactly.
And so in some of those places, water is the most important factor. But I bet my guess is it's probably important in the whole region. Just
yeah, it would be interesting to see.
I'm surprised there's also peppering bread sites in the Amazon, for example, which would be temperature.
I'm expecting that to be wrong. I don't know why, but they shouldn't be there.
But in our previous study, though, light was a big deal in the Amazon, right?
In terms of leaf gain, but it's just looking at loss.
Yeah, so you don't get situations where the light drops, causing the bottom layer of leaves to go into.
Well, this says there are some situations where you do, but I wouldn't expect it to. Especially because there's no coherent region where you think, oh, this is some kind of thing. So they just.
But I wonder if that might be another thing. So it'd be good to talk about this, because I suspect if you looked at something a little bit less black and white, or red, blue, and green, but looked at something that was a bit more blended, it might well be that what you've actually got is the light. Because if they go up to the compensation point in the dry season, then by definition in the cloudy season they'll be below the compensation point. So then they may drop again.
Yeah. Yeah, it's a good point. Yeah, we can talk about this.
Yeah, it'll be a little extension.
See what it looks like. Another thing, which I don't know how much I can trust, is the growing season length. So how long is a favorable season in which they can keep leaves? And luckily, luckily, my model works for tropical regions. It's continuous, so there's no strictly unfavorable season. And then you can see that you have a longer growing season for deciduous areas, and then the season gets shorter with higher latitudes.
Yeah.
But my doubts about this map is it looks like it's fairly heterogeneous at high latitudes. So I don't know if that's actually information about the different types of species or response to what's there, or is just something that comes out of the way I've built the model.
You have the evergreen boreal type species in there at the moment, like do you have species that don't care about temperature, that sort of ride out the winter?
Well, they should be, but because of the way the evergreen data looks like, it's not.
So I think given that makes sense to me, because then what this is supposed to show is what this actually should be showing is the growing season length for deciduous trees up there.
Yeah.
And actually, firstly, I think the numbers in general look about right with 50 to 100 days up there. That sounds pretty good. And secondly, it probably could be quite variable place to place, I suppose. I mean, temperatures and...
Which should have jumped from like 50 to 300?
So it's like 100 to 300.
Yeah.
Within 2 degrees.
Yeah.
It would be really cool to take, for example, a point that you know is definitely boreal forest there, include that as a strong prior, and estimate the error in the MODIS data throughout that time series to then use as a mask for, for the snow affected regions. So you won't have anything else to enable evidence to distinguish between different vegetation types.
Yeah, that's a good point.
Because again, the eastern US looks a little, not again because it didn't look last time, but it looks kind of sus. I mean,
it looks a bit too long.
Well, it looks a bit too, as Mark said, abrupt.
Yeah.
From within 2 degrees. I mean, literally, unless my eyes are playing tricks on me, and I think they have been through your whole thing because I've been struggling with colors, but I mean, it literally looks like you go from 100 to 300 in 2 degrees.
Yeah, it does.
And not even latitude, but longitude.
So how do the parameters work in cell? Are they the same? They're the same everywhere, right? The same parameters are applying in each grid cell.
I fitted parameters individually to every grid cell, hence the heterogeneity.
Right. Oh, that's probably it then. So I think so. Probably the next thing to do would be to see if you can do the opposite and have
one.
Because in a way you sort of want the same parameters everywhere. Well, no, you can see different there are arguments both ways. Yeah, but I think to do both makes sense. Yeah. I mean because the problem when you do this for prediction, then you'd actually carry over something special about that grid cell. So you'd actually say, oh, I need the parameters for that grid cell, and so whereas in a way you kind of just want the climate. Then of course on the other hand, someone could say, well, no, grid cells are different because they've got different vegetation right now. So actually, there will be different. So I think So
it depends. I think you'll have some parameters that you need to fit to every grid cell.
Yeah.
That's why you don't. But yeah, that is one next step.
I would love it to infer a evergreen tropical rainforest strategy based on all of the data, which has common parameters. See how well it does across tropical regions. Then take tropical deciduous. How similar are the parameters you infer for tropical deciduous compared to tropical evergreen? How well does that do? And then boreal, well, the data's pretty crummy with boreal. It's for temperate deciduous.
Yeah.
And are there things that are common to the different strategies or noticeably?
Because you can plot this map with just MODIS data.
Yeah. Well, then you have to define growing season more artificially, because I know when they drop leaves and when they gain them here. Well, with the MODIS data, you'd have to say, well, when it goes over one LAI,
I mean, but presumably there were some threshold points that were pretty non-arbitrary within those distributions that you showed in the first couple of slides. And if you just cut that and made the map, one would presume it would look significantly smoother.
It would probably.
But it's quite interesting in a way, given that, in a sense, how smooth that looks, given that you parameterize it separately for every grid cell. Yeah, I mean, it shows there's quite a lot of information there because it doesn't look, although it is a bit noisy and heterogeneous, it's also clearly got a structure to it as well. Right? You can see that from the data.
It's picking up a lot of the information by introducing a lot more
Yeah.
Yeah.
So that's an obvious next step for me is to then see if we can get away with fewer or even no grid cell specific parameters.
Yeah.
So of the 12 parameters that you have, how many are potentially generic?
Oh, no idea. So compensation points probably not, because I think those vary from species to species quite a lot, and photostatic capacity does vary. Things like water stress, maybe, unless you have species that are really adapted to low water. Okay, so the answer is I don't know. I'm just making it up on the spot.
No,
I don't know.
I would thought compensation. I mean, there's ones that they've used traditionally that it's had a good discrimination power. So aridity index.
Yeah.
It seems to do well at distinguishing between dry lands and the dry deciduous and non-dry deciduous regions for lots of regions of the Earth. So you might expect a parameter there.
There's a halfway house, isn't there, which is if you can't make the parameters of this model themselves independent of grid cell. So like for the compensation point, you've either got one that applies to the whole world, or you've got one in every grid cell. That's quite an extreme. And in between, you could have that as a function of climate.
Probably, yeah.
2 or 3. So again, that would be a potential extension then. So you just sort of say, look, we can't explain why, but we infer that things like the compensation point do themselves have a pattern against the climate.
Yeah, and that could possibly be useful for predicting stuff that will happen in the future, because as it is with these parameters, if you have any scenarios, you're assuming that the vegetation type stays the same and all parameter values still stay the same, whereas if some of your parameters were themselves a function of something else, then they'll be more flexible for changing vegetation.
And you could have a time scale of response there as well, because when you think of average temperature and average precipitation, you could define that over a period. If you define it over a year, the parameters will rearrange themselves very quickly. If you define it over a century, that's the idea of vegetation is taking longer. So that'll all be really interesting.
Yeah, that will be. And you can also look at some time series. These are the same locations from my examples. So for the tropical wet, there is a problem at the start, and I think that's a spin-up problem, because the leaf age will be longer. So I haven't spinned up the model properly, but it does capture the single cycle after that. And then for the dry region, it does capture pretty much everything. For temperate regions, if you remember when I showed the difference between the data and MODIS, the mean was lower, and it doesn't capture the peak in summer. I don't know why at the moment, I just know it doesn't. And for the evergreen, it does its best, but I don't know what that means. It tries to, but overall, it's in the region where it's supposed to be, and you do get a good fit. Yeah. And that's all I have for now. So this far, I've built a global phenology model that predicts leaf loss and leaf gain in terms of incoming light, temperature, and soil moisture. And it can predict various limitations across the globe and growing season. And for the next step, we will try to implement the results of my model into global carbon and climate models and see if it does have any impact and if it can improve results and predictions, and try to see how phenology will change with climate change, which is quite a big question. That's me.
Cool.